Thank you very much. It's really a great privilege to speak here. It has just to excuse myself, or I'll explain a bit how this came about. Last year, Nima was in Seoul and stayed for one day. I guess you came in the morning and left in the evening, right? And gave this extremely inspiring talk about, as I understood it, whether algebra or geometry is more fundamental. Right? And the conclusion at the end is that somehow combinatorics is more fundamental than either, right? And so since I work on arithmetic geometry, I feel like somehow I work on geometry that somehow algebraic, combinatorial, and geometric at the same time, and I hope that might interest him a little bit. But another problem is that I originally prepared it just to talk to Nima and maybe a few other people who are interested, and then it was announced as a seminar, so I very hurriedly
It's an informal seminar.
That's right, okay, anyways. That's right. So I superimposed the original presentation with a colloquium talk I gave at Perimeter last week. And there they asked me to prepare for physics graduate students. So if you superimpose Nima and a physics graduate student, I'm not sure what you get. So feel free to leave anytime you feel this is irrelevant. Anyways, let me start out with a very brief remarks on what you know very well, which is this use of principal bundles in geometry in many ways, or occurrence of principal bundles. So typically, you might start with a connected orientable manifold and some Lie group. Of course, for many reasons, we're interested in the space of principal G bundles with connections on them. In gauge theory, of course, you study functions defined on the space of connection. It might be the Yang-Mills function in 4 dimensions, the Chern-Simons function on a 3-manifold, or you might decorate it with many other fields and so on. From the point of view of geometry, probably the main thing that's been of interest is the space of solutions. Right? So study of critical points will give rise to Euler-Lagrange equation whose space of solutions form moduli spaces. Now, these moduli spaces, you might be interested in them for their own right. For example, you might be interested in specific solutions if you're really interested in applications. But for geometers, there's a sense in which these moduli spaces themselves are like cohomological invariants of the manifold. And this has been a very powerful idea. It's sort of like non-abelian cohomology, the space of solutions to a nonlinear differential equation on M. So of course, this inspired Donaldson theory, Simpson theory, Seiberg-Witten theory, and led on to TQFT and so on. In the direction of TQFT, very grudgingly, geometers started getting interested in these integrals, right? It was very hard for them. It's hard for people like me, even harder. The idea that somehow you could take, say, action functions, exponentiate them, and integrate over some terrible space like spaces of connections, or even throw in these kind of local operators and do path integrals. So as I said, most everybody in here knows much more about this than I do. I have a very primitive understanding of these things. Nevertheless, I've been very tempted by the thought that one could try to develop tools like this for the study of arithmetic schemes, not just manifolds over the real complex numbers. What I might mean by this subject and such tools. So let me briefly remind you what I mean by arithmetic schemes, first of all, to set up the kind of problems that I might be trying to address. So an arithmetic scheme, these are finite unions of spectra of rings that are sometimes called absolutely finitely generated rings. So let me explain the rings first. An absolutely finitely generated ring means literally just a ring that can be generated just using polynomial operations by a finite collection of numbers. So you can say it's a ring that's a quotient of a polynomial ring over the integers. Right? So the obvious examples are the integers themselves. If you're an algebraic number theorist, you might be interested in things like algebraic number fields, like Q with the square root of -1 throw in it. That has a ring of integers in it, that's sometimes called the Gaussian integers. That's a typical model you can keep in mind when thinking about algebraic integers. Or you might think about ring of functions defined over Z on an elliptic curve. That's what this example is. Or it might even be a completely random ring. You just take whatever numbers you want, complex numbers you want, and look at the ring that they generate. Yeah? So one intuition about rings of this sort is that these are, in some sense, the only rings you'll actually encounter in practice. Right? Because you need a certain collection of numbers. Whenever you admit a certain collection of numbers, you need to be able to multiply them and add them and so on. But it's very rare that in practice you need infinitely many generators somehow. Of course, you still need it for theoretical purposes, these very large rings and fields that are idealizations of experience in some sense, right? But for practical purposes, these kind of rings, absolutely finitely generated rings, are the ones you use. So in particular, for example, some of you are interested in complex algebraic varieties. You might be interested in Calabi-Yau manifolds, for example, right? Calabi-Yau variety. So all of these things are actually have an underlying arithmetic scheme structure. Because, for example, you can view it as, given that the coefficients can be viewed as running inside a absolutely finitely generated ring. Right? So that it's parameterized by such a ring, again, by absolutely finitely generated fibers. So, and somehow, I think it would be very nice if this arithmetic scheme structure can be made to play a role in problems of interest for geometers. Well, it does, that I know, but maybe it's even of interest to physicists. That would be very interesting. Just to briefly remind you, so of course, some of you will know this very well, and otherwise this might be too brief, but the spectrum of a ring, you can think of it as prime ideals or suitable equivalence classes of maps to fields. Right? So actually, that second point of view, in a way, this is a trivial remark, but I think it's kind of attractive to think of it that way, because it does remind you a little bit of physics. If A is an algebra of observables, such algebra homomorphisms will be something like pure states, right? So that's one way you can set theoretically think about the spectrum. But the point is that the theory of schemes starts from the fact that somehow associated to such a ring, there's a geometry that's called a spectrum. It's a set theoretically, it's just sets of states like that, right? But there's also a geometry that's set up in such a way that homomorphisms of ring correspond to map of spaces going in the opposite direction. Because, of course, functions on this guy can be pulled back to functions on this. The general idea is A consists of functions on spectrum of A. Right? Sure.
Why not homomorphisms to what do you call them? Principal ideal domains where you have.
Oh, you can do that as well. That's right. But if you have a homomorphism to a principal ideal domain, it will also go to its fraction field. Right? So you can associate one of these naturally to one of your homomorphisms, and the equivalence relation I didn't spell out sort of takes care of all those things as well. Okay. Now, a scheme is a more global object that you glue out of these spectra of rings. So that's a brief course on scheme theory. Right. Now, so since I told you what these objects are, just to explain what I mean by trying to use the kind of tools that people used in gauge theory in this context. So the idea is that even given an arithmetic scheme, you can try to study sheaves on such things. The scheme itself, of course, we're interested in its geometry, arithmetic geometry, but also sheaves on them and moduli of such sheaves, right? So that eventually, I'd like to study action functionals on moduli spaces of sheaves on arithmetic schemes, as well as path integrals. Now, as I said, I barely know what these means, but at least I have a few examples now of this situation that seems to make sense and not be totally uninteresting, so I thought I'd introduce that to you. These local functions, by the way, in number theory, so, well, these moduli space and local functions, just say a few more words at the outset about them. The moduli spaces that are most of interest are things that people call moduli of Galois representations. So these are things like Galois groups of Q bar over Qs, these kind of fields, automorphism groups of fields that arise naturally in number theory, and we're interested in their representations. And in some sense, studying their moduli has been very important in number theory and arithmetic geometry for the last 2 decades or so. Like, to an extent, the proof of Fermat's last theorem and the Shimura-Taniyama conjecture relies on the study of those moduli spaces in a very local form. But I feel that the global study of these moduli spaces is still not very much developed, and it would be interesting to view them in the manner that, say, geometers and physicists look at them, and maybe try to be inspired by ideas from physics the same way geometers have been. These functions, these local observables, for example, have been, again, very much studied in number theory, but from a different point of view. It's trying kind of a pretentious point of view from the point of view of number theory. What they are, the typical one we're interested in, is these Galois groups tend to contain special elements corresponding to prime, called Frobenius elements. And so we can take traces of those things in representations, which will give us things that are like Wilson loops in three-manifold theory or other field theory. So again, these are extremely well studied, except not from this point of view in number theory.
Since
So,
you're only integrating over space of representation,
right.
naively, that's analogous to integrating over spaces of classical.
Just classical solutions. That's true too. You're right. Yeah. So at the moment, these are classical solutions to a certain extent, but it slightly depends on your point of view. There's a way in which, so a point of view which is just kind of empty philosophy at this point is that inside these representations, you will have things that are, you might call motivic representations, things that come from geometry. And for me, those feel like really the classical solution to some extent. But that's just, as I said, it's just empty philosophy. But another thing you can do, which I won't do today, but that'll come later, you can take global representations of these global Galois groups and put them inside collections of local representations of local Galois groups. So if you have a random collection of local Galois representations, you can view those as being like distributional connections. So the quantum field theoretic distributional connection of the sort that comes up in constructive field theory or something. So that's the other off-shell fields that you might consider in this situation. But for the moment, I'm going to be very conservative and just, because this is already, for me, interesting enough. Although, again, I recognize that it's very primitive from a physicist's point of view. Right. So, as I said, these local functions have been very much studied in some sense, but there's only one concrete example that I know of a global action functional, and I'm going to describe them in the subsequent slides. So to get to that story, even though it's not strictly necessary, I'll just give a brief introduction to a topic that some people like, some people think is completely stupid. I used to be the latter, and I'm moving over to the former. It's called the arithmetic topology. It was started more or less in the 1960s. Barry Mazur and Mumford and people like this drew a certain analogies between number theory and the study of three manifolds, right? And that more or less developed into a subject called arithmetic topology. And I started getting interested in it about 10 years ago from, to my mind, a slightly different point of view from what came before. But in order to introduce this subject, let me just briefly give you some examples anyways and try to give you a feeling for what a fundamental group of a scheme is. Now, there's a very coherent, harmonious theory of these things where you develop it in a categorical fashion very similar to the classical theory of fundamental groups. I'm not going to do that today, just give you kind of working man's definitions. Right? So for example, so if you have a spectrum of a field, its fundamental group is just this absolute Galois group. The Galois group of the separable closure of the field. So over a characteristic zero field is an algebraic closure. So for example, the Galois group, the fundamental group of the spectrum of Q is just the so-called absolute Galois group of Q, the automorphism group of all algebraic numbers. All of these things can be proved as theorems, but they based upon more harmonious foundations. Now, in order to go a little bit further, I need to introduce just a little bit more algebraic number theory, which I'll try to do in a formal and informal way. So we're mostly going to be interested in algebraic number fields and rings of integers, algebraic integers inside them. And sometimes you say a finite extension of a field, if you have one algebraic number field sitting inside another, we say the extension field is unramified. If when you look at the algebraic integers in the bigger field and view it as an algebra over the algebraic integers in the smaller field, then the relative Kähler differentials are zero. One can make sense of this in a purely algebraic way, but the more kind of algebraic number theorist way of thinking about it is you consider the primes inside the smaller field, and because you're going to a smaller ring, and since you're going to a bigger ring, it has potential to be no longer a prime. That happens very often. So primes split inside these larger rings. And we say it's unramified if the field extension is unramified. If this ring, when you split the primes in the smaller ring, there's no multiplicity. They all split into distinct primes. And the reason I'm mentioning this is that when so this is a non-example, I forgot. So if you take this example I said at the beginning as viewed as an example, as an extension of Q, is a non-example because the prime 2 splits up into a square of a single prime inside the Gaussian integer. So this is a ramification. This is an example of this can called ramification. If that never happens for any prime, we say it's unramified. So for example, if there's a slightly different example, if you go already to the field obtained by square root of -5 and then go to the bigger field where you also join I, then this actually ends up being unramified. The ramification is somehow eaten up by the smaller field.
Could you unpack the first formula of the previous transparency for me just a little bit? Spectrum of a field is all the prime ideals in the field, so that's
just a point. It's just a point. That's right.
pi1 of a point is now a complicated analog group.
That's right. Yeah. So that's exactly why. That's the way you have to set up this category, that the functions on your point are already part of the geometry of the space. So it's not, it's the underlying set is only a kind of pale reflection of the full geometry we're considering. So the category of maps between them and so on all take into account the functions, which in the case of spectrum of Q is Q itself. Yeah. So I'm not doing full justice to the theory, but anyways, the functions are part of the geometry. I think that's one way of answering your question, if it's an answer. Yeah. Well, thank you. But all of these are very confusing points, actually, when you're first studying scheme theory.
But at least if I have like a subfield of a field, I
Right.
get a map from this point to that point.
Yeah, that's
and
true.
it induces a map on the pi1s.
That's right. Yeah. So all of those things happen. This has the pi ones here have all the nice functorial properties that you expect for topological spaces. I was going to mention another example. Forget about it. It's too complicated. But the reason I mentioned this is that if you take rings of integers inside these algebraic number fields, its pi1 is also a Galois group. But if you take the fundamental group of spec F, you get the Galois group of the algebraic closure of F. But instead, you just take a much smaller field. That is the maximal extension, largest possible extension that's unramified. That somehow corresponds to being local homeomorphisms everywhere, an algebraic notion of that. Yeah. So that's what you get as the fundamental group of the spectrum of the ring of integers inside the field. So by the way, so I say these things, I describe these things blithely, but they're actually very difficult to compute, and it's a major problem, I think, in sort of non-abelian algebraic number theory to be able to compute these things. There are very few examples actually computed. The abelianization of these groups are isomorphic, that's called class field theory, to something called the ideal class group. Those are computed, and we know how to compute those. But these full fundamental groups are very hard to compute. They're sometimes finite, a lot of the times infinite. And so it's something that's still a quite mysterious object in number theory. Maybe just one more computation or assertion about what a fundamental group is. What you can do is you can take the spectrum of one of these ring of integers and take away a finite set of primes. Yeah, so it's like removing some points, right? But actually, it's more like removing knots, as I'll explain in a second. And you say that the field extension is unramified outside S. Well, there's a Kähler differential criterion, but another way of saying it is that the primes in F that are not in your your finite collection, they don't have any ramification. They only split into distinct primes. So for example, if you look at this extension I mentioned, it was the 2 had multiplicity when you decomposed it inside the Gaussian integers, but if you remove 2, it's unramified actually. The 2 is the only one that has the property, so this extension is unramified outside 2. More generally, if you join the square root of d to the rationals, then you get an extension that's unramified outside 2 and all the primes dividing that d. So this is the kind of flavor of what these unramified extensions are like. And so then as far as fundamental groups are concerned, so if you remove these finitely many primes from the spectrum of a ring of integers and take its fundamental group, then what you get is the Galois group of the largest possible extension that's unramified outside S. It is also a relatively mysterious object in number theory. Right. So this is a quick review of algebraic integers and fundamental groups. Now let's move on to the analogy, this arithmetic topology business that I mentioned that the people initiated in the 1960s. So start with an algebraic number field with a ring of integers. Right? So the analogy that Mazur and Mumford proposed is that the spectrum of the ring of integers should be like a 3-manifold. And I'll try to explain in various different ways why people thought this. Right? Right now, I'll just assert this, and then we'll move on to the rest of the analogy and come back to this. Now, if you have a non-zero prime ideal inside this ring of integers, for example, an ordinary prime inside the integers, right? You can take the quotient ring, yeah? Then that becomes a so-called finite field. because that's also a maximum idea. You get a finite field as a quotient of one of these ring of integers. So if you take this quotient map, the map of spectrums go the other way around. So you get an embedding of the spectrum of a finite field into the spectrum of one of these ring of integers. And that's viewed as being analogous to the inclusion of a knot inside the three-manifold. Why a knot? So this is sort of the beginning, really, of the analogy. Why is that like a knot? It's because the fundamental group of spectrum of a finite field, remember, it's just the Galois group, absolute Galois group of the field. But for a finite field, the absolute Galois group is just topologically generated by one element. It's called the Frobenius element. Yeah, that takes an algebraic number and just raises it to the power equal to the cardinality. So for example, if Fv is Fp, the finite field with p element, is just a pth power map that generates the whole Galois group, absolute Galois group. So it's like just a copy of Z. So it's like k pi z hat 1. So it's like a circle. So that's the general idea. So the way it's sitting inside the ring of integers is supposed to be like a circle inside the three-manifold, and therefore like a knot. So that's, as I said, the first mildly substantial step of the analogy. Maybe I'll also briefly remark that if you take the generator here and using this mysterious functoriality that he didn't really explain and put it inside the fundamental group of X, that element is sometimes called the Frobenius element of the prime, now sitting inside the fundamental group of the ring of integers. Right. Now, so here I'll get slightly more technical. Whenever you have one of these number fields, you can complete them at various absolute values. Whenever you pick a prime inside the algebraic number field, you can complete the field and its ring of integers. And the completion of the ring of integers is viewed as being like a solid torus around the knot, whereas the completion of the field is viewed as being taking the solid torus and deleting the knot in the middle, which therefore is homotopic to the boundary. And so that's sort of like a knotted torus. So that's the view that comes up in this analogy. The reason that that's viewed like a solid torus is because that completion, well, you see, it's algebraically you express it as an inverse limit over these powers of the prime ideals that define your point, that define your knot, so to speak, right? And that's like an algebraic tubular neighborhood of your prime. Yeah? And so that's the sense in which it should be viewed as topologically equivalent to a solid torus around your knot. It's like there's an algebraic construction of a tubular neighborhood. Meanwhile, the field is obtained by there just by inverting the generator of the maximal ideal of that. But of course, the maximal idea is exactly what cuts out the knot in the middle. So that's like deleting the knot. Okay? So this, once again, the completion of the ring of integers is like a solid torus around the knot. The completion of the field itself is like the boundary of the solid torus. Finally, well, if this thing that we already considered, taking the spectrum of ring of integers and removing finitely many primes, that's like deleting finitely many knots. That's homotopic to deleting the whole solid torus as well, right? So this will be like a three-manifold with boundary that are like tori. That's the way this analogy continues. And the Galois group, of course, this fundamental group that I mentioned is supposed to be like fundamental group of a three-manifold with boundary, while the fundamental group of this completed fields, remember, this is like pi 1 of the boundary components, these tori boundary components. And the last part of this analogy I'll mention is that if you remove sufficiently many primes, this should be like a hyperbolic three-manifold. So this is an idea that informs this arithmetic topology, and also some of these speculations of Grothendieck in the 1980s surrounding fundamental groups of schemes somehow draws on this intuition that this number fields, ring of integers in number fields should be like hyperbolic three-manifold in sufficiently complex cases. Okay, so that's a lightning review of this analogy. But actually, so what got me interested in this subject is not so much this analogy itself, but what you might call a dual view of the analogy. So what do I mean? Well, already we discussed this, right? What number theorists are actually interested in a lot of the time are these spaces of representations. That is, you take fundamental groups of one of these ring of integers with finitely many primes removed. So this will be a Galois group of an extension of the maximal extension where ramification is only allowed in finitely many places, right? And you're interested in these representations mapped to some kind of a group. That might be a finite group. It might be GLNC. It might be GLN of the p-adding numbers, something like that. It might be a p-adding Lie group. So there are a number of targets possible, but it's certainly reasonable to consider the space of all such representations. How to turn it into a space can be a delicate matter depending somewhat on what kind of A you have, but certainly the intuition that it's a space should be obvious to most people, most geometers. And then, in differential geometry, we already discussed the fact that on spaces of that sort, you have these Wilson loop functionals, right? And again, in the arithmetic setting, if you choose a prime inside that scheme, the ring of S integers, integers with primes removed, and a representation of A, right? Then you can consider the function on the space of representation that associates to a representation the trace of the Frobenius element at V in that representation. That gives you a function on space of representation. So somehow, my point is that rather than this analogy between three manifolds, rings of integers, primes and knots, what you should be focusing more on is analogy between these kind of spaces and spaces of solutions to Euler-Lagrange equations, and especially from the point of view of the kind of functions we study on them. This seems to be a more important analogy than the bare schemes themselves.
Sorry, you said it already. This is the analog of the Wilson loop?
That's right, yeah. This is the analog of the Wilson loop, exactly. So that's what I view as the more fundamental analogy between bundles with connections and Galois representations, and especially natural functions on their moduli. The natural functions can be rather complicated. For example, it might include examples like this, right? What would come up in things like the colored Jones polynomial, right? You can take one fixed representation, take all its symmetric powers, right? And take traces, Wilson loop type functions on such things, right? If you do that, you get 1 over this determinant of 1 minus type of gadget. This is the kind of thing you'll come up often as Euler factors inside L functions, so-called, right? Those come up also naturally as Wilson loop type functions inside sufficiently complicated representation. But, of course, all the examples of this sort were all local functions, right? So I'm now going to go ahead and try to describe an example of a global function on the space of representation, which to me looks to be interesting. So this is the Chern-Simons function, or rather the Dijkgraaf-Witten function that I'm about to go on to describe. So in order to do that, I'm going to use this only in a limited way, but I'll just very briefly remind you about group cohomology. So how that is defined? You have some topological group G acting on some other topological group E, mostly sometimes you consider non-abelian E. Actually, I'm more interested in non-abelian E, but abelian is the one that's usually studied. And then there are these group cochains. These are simply functions, continuous functions from powers of E, G to E, the Cartesian products of G to E. And you can form a complex out of this in a kind of predictable way that you can figure out if you think about it a little bit. That the C0, these are just E itself, elements of E itself, since it's zeroth power. Then C1 is just functions from G, and C2 is two variable functions from G, and so on. And you can define a differential between these functions that turns this whole thing into a complex, right? And if you do it this carefully, then you get a complex in the sense that D squared is 0. Right. So it makes sense to consider the kernel of one of these Ds, right, which we call Zi, and the image of the previous term, which we call Bi, by tradition. And the group cohomology is just defined to be the ith kernel modulo the ith image. So that's the way you define cohomology of a group acting on a moduli. So for example, when you do this for a manifold, the H1 of a manifold can be computed in terms of the group cohomology of its fundamental group. So this is kind of a convenient fact that comes up sometime. But a higher cohomology of the group maps to the cohomology of the manifold, but in general, these are not equal. So, unless M is a k pi 1 or something. And another kind of simple fact is that if the G action on E is trivial, this cohomology becomes the same as homomorphisms from E. So these are all kind of basic facts from group cohomology. Now I'll move on to the discussion of the global functional. One can go on to generalize this to periodic Lie groups. So for the moment, for this lecture, I'm only going to describe this in the case of finite coefficients. That is, and we need some assumptions to set off. I now know how to get rid of this, but it's a bit elaborate. So we'll start with a simplifying assumption. Well, I'm going to assume that F is a field that contains the nth roots of unity. So e to the 2 pi I over n. So it's an algebraic number field that contains the nth roots of unity. And X is, as per our previous notation, is the spectrum of the ring of integers. And one basic fact, so I'm going to state a bunch of facts about the cohomology of these spaces. And here, I'm referring to something called étale cohomology that I haven't explained at all. It's very close to the group cohomology previously defined. It's not exactly the same. Closely related, but it's something that's very much like topological cohomology of manifolds in this slightly more abstract setting. And the basic fact about this space, which is sort of at the foundation of the analogy with 3 manifold, is that higher cohomology is all 0, actually. And H3 is the one-dimensional in some sense, in this sense. Yeah? Now, what underlies this is a slightly more basic fact, is that when you consider étale cohomology of schemes of this sort, so GM here refers to the sheaf of invertible functions. Yeah? So for any open set, you consider invertible functions. And there, if you consider H3 with that sheaf, you get Q mod Z, you get this big torsion group. So these kind of torsion groups arise quite a lot inside this theory, which makes it somewhat different from topology. But you should think of this as being the torsion points inside S1. So it's come out a discrete torsion version of the kind of thing you find in topology if you consider S1 coefficients.
Invertible functions here are invertible elements of F?
Invertible elements of OF, that's right. So if you take an open set of OF, you would consider invertible functions on those things. So you only allow denominators outside the primes in the primes that you are removing, for example. So this is the sheaf. Is that okay? Right. So yeah, so these are kind of difficult sheaves to get used to, but once you do that, you come up with computations like this. So I'll remind you, for example, for a complex manifold, if you look at H1 with the coefficients in invertible functions, you get exactly the holomorphic line bundles, right? Yeah. But it's interesting that these holomorphic line bundles, I mean, some of you know this better than I do, I'm sure, is that there's something topological about this space as well. So for example, if you have a compact Kähler manifold, then the connected component of this space consisting of holomorphic line bundles with trivial Chern is just the same as S1 coefficient H1, right? Which is a topological thing. Yeah? So this is a consequence of Hodge theory, of course. So even over complex manifolds, this kind of thing that seems to consider these sheaves of analytic functions and so on, but it's actually quite topological in nature. Yeah? And that's what happens over here. Invertible functions give you a very discrete type of answer that's like the discrete points of the circle. So I guess what I'm trying to say is that GM business is very much like S1 coefficients that you might consider in manifold theory. Right. This H3 thing, maybe I'll just briefly mention. Again, these are all black boxes at this point. But the H3 computation actually ultimately relies on something called the local computation of the local Brouwer group. Remember, this pi b was the Galois group of this local fields, the completion of F. So it might be a Galois group of QP, for example, right? So these things, except when you take completion at the real places, I should have said this means, when I write V, I mean anything but the Archimedean place. On any other completion, if you compute this H2, you get exactly this Q mod Z. This classifies, well, there are many descriptions of the thing. It classifies central simple algebras over your local field. It classifies things that are called Brouwer-Severi varieties, things that are isomorphic to projective space over the algebraic closure, but not over your ground field, like conics without a point. Right? They classify other things as well. If you like, they classify GM gerbs, right? But their classification is given by a single number, mod Z. A rational number mod Z. So this is called the invariant of a local Brouwer group. And when you want to compute the global thing, like the corresponding thing with one of these fundamental groups of rings of S integers, they fit into an exact sequence like this. So you map remember these local groups mapped to the global thing by functoriality. So you get this exact sequence where the global elements mapped to collections of local elements. These are all Q mod Z. So you can sum them to get a single Q mod Z, and you get a short exact sequence like this. It's called the reciprocity sequence in class field theory. And this Q mod Z at the end is essentially the previous H3. So that's the way to understand that Q mod Z occurring in the comparison with three manifold theory. Now, I realize that I'm just laying a whole lot of algebraic number theory on you. But if it's any consolation, these two statements here, this local Brouwer group computation and this exact sequence, more or less is the full conceptual content of class field theory. So those of you who have ever been interested in class field theory, I don't know how many of you have, is if you understand these two exact sequences, the conceptual content is all there. These are the most important part. And then you have to interpret them in specific ways to apply them to actual number theoretic problem. But the local Brouwer group computation and this reciprocity sequence is class field theory. And I'm summarizing all of that in a slide. So it's a bit much, but anyways. Yeah. So now I'll define the Chern-Simons functional, right? Using the fact that I mentioned earlier, this group cohomology, pi1 group cohomology maps to that H3 at tau cohomology. And we said that is canonically 1 over n z mod z. That's also z mod n, but somehow because it's inside Q mod z, it's convenient to write it in this way. So how do we get Chern-Simons or Dijkgraaf-Witten type functions? As I said, I'm just going to work with finite group coefficients today. Like, let's take A to be a finite group. So I'm taking the moduli space of representations of the fundamental group of X inside A, homomorphisms to A mod conjugation, right? In order to define a function on these, a global function on these things, we need, as in the Dijkgraaf-Witten theory, choice of a cohomology class. But this is nothing arithmetic, right? This is just that finite group A, choose a cohomology class with Z mod n coefficient. Nothing, so it's just a discrete collection depending only on the finite group, right? Discrete bit of data. Now, so once with this choice, now we know it's obvious what to do as in the three manifold case. Given a representation, right? What do? We use the representation to pull that back to a cohomology class of pi1, which then maps to this tau cohomology thing. This sorry, I should have written that in the middle. H3 of X with Z mod n coefficient. Then this, which has an invariant inside Q mod Z, which for this is a 1 over n Z mod Z. So that's a function. That's all there is to it. So it exactly imitates what occurred in the Dijkgraaf-Witten theory, right? Except just using the cohomology of these rings of integers rather than three manifolds. So I'll show you just one example, one concrete example, because I can't do too many computations with this yet. Unfortunately for this, I need the n square roots of unity to be in F. So roughly speaking, the reason these conditions come in is because you need these roots of unity to fix an orientation. So that's the general reason that these conditions come in. And we'll just take A to be Z mod n. So in that case, remember, the pi1 action now I'm considering is trivial. So H1 just becomes homomorphism. This homomorphism is the same as this cohomology H1. This moduli space can be viewed as the space of homomorphisms. And because the target is abelian, it just factors through the abelianization of pi1. And I stated without any proof earlier that the abelianization of pi1 is simply the ideal class group. So these are just the dual of the ideal class group. That's all this is, the space of representation in this case. And so this is a finite group that can be explicitly computed given an algebraic number field. So that's the space of representations we're considering this case. What about the cohomology class C that we need as input for the function? Oh, I guess I should have said. So this is the ideal class group. And this isomorphism between this ideal class group and the abelianized pi1 is called unramified class field theory. It's essentially induced by this thing that I mentioned earlier that takes a prime to the Frobenius element inside the Galois group at that prime. Now, we'll take the cohomology class constructed in a simple way as follows. Oh, sorry, this should have been Z mod n as well. It's slightly confusing notation. So what we'll do is, remember, now A is itself Z mod n, so you get an element of H1 just by considering the identity map from Z mod n to Z mod n. That I'm calling A. Right? On the other hand, this exact sequence gives rise to a Box-Stein map, so-called, that goes from H1 to H2. Right? So we can take the product of the two classes and get an H3 class. That's what C is in this example. So using that, I get a Chern-Simons function on a billion representations, right, with targets and more than. And if you compute what I said over here is exactly this. You just pull back the class A, pull back the Box-Stein of A, and take the invariant after taking co-products. You'll see this looks exactly like the abelian Chern-Simons integral that you see in three-manifold theory, but in a slightly different form, where the Box-Stein plays the role of the differential. And that seems to be a common thing in this arithmetic version of the subject. Box-Stein operators are very much like differentials of derivatives of, exterior derivatives of differential forms. Okay, so I'll show you the one computation I know how to do. Sorry?
But that particular statement is essentially true in geometry.
Actually, I don't understand that very well. Could you explain that to me later? Actually, I vaguely understand what you mean, but I get confused by this.
You might find my explanation equally.
Okay, yeah, but anyway, okay. So, by the way, that statement, for me, that statement was inspired by the fact that exactly that happens in something called crystalline cohomology for varieties over finite fields. But that's another story somehow. That's one way you define differential forms on crystalline on varieties over finite fields. Characteristic zero differential forms. Okay. Now, of course, I've just spoken about Chern-Simons functionals on Galois representations, right? So, but of course, the invariant, we have to do a path integral. So this is the sort of main finite arithmetic path integral I mentioned in the title, right? But we can also throw in linear terms, right? Because remember, for any finite collection of primes, they define by this reciprocity map, right? Elements inside the Galois group, which we can then apply the representation to, and we get a number again. And then we exponentiate it. So this will be an nth root of unity, the whole thing, right? And you sum over representations. So this is a kind of a billion path integral with insertion of some Wilson lines, Wilson loops.
Sorry, what is rest of PJ?
Oh, sorry. So this was this reciprocity map. They took ideals to elements of the Galois group.
Corresponding to the Frobenius.
For corresponding to the Frobenius, exactly. That's right. That's right. So this is this rec is exactly the Frobenius at that prime. Right. Yeah. Okay. So I'll show you how one computes this. This is kind of trivial. It's almost tautological, actually. But at least when n is a prime. When n is not a prime, it's already reasonably hard to compute that integral. And certainly, of course, we can write down that integral for non-abelian representations as well. But I can't get anything interesting out of the formula, so I haven't really computed much with it. But in this case, what happens is this. So this is the sum over all representations again. So this is the finite path, the arithmetic path integral, right? And then you get a formula like this. So let me explain the terms a little bit. I'll return to this formula after explaining the terms. But of course, I'm sure this will look very familiar to people who've done the path integral over in abelian Chern-Simons theory over three manifolds. So that D that occurs here, I took a determinant of something. So that's like that Box-Stein operator, except you have to modify it a little bit. So this is another black box that I'm not going to explain. But if you take the previous Box-Stein map and compose it with a map of sheaves to something called the sheaf of p roots of unity, you need to compute it in slightly different cohomology called flat cohomology rather than the tau cohomology. You get something that really is like the map from one form to two forms, because that H2 there ends up being exactly the dual of H1, like two forms are dual to one form. So it really goes from one vector space to its dual. Right?
Can you say, what does this thing depend on? Depends on your choice of P and that collection of PJ?
This formula.
Yeah,
that's right, yeah, that's right. That's right, that's it, yeah. And the number field, of course.
Right.
The number field. Yeah. Thank you. So that's right. So now this is a map from H1 to its dual. So that's a quadratic form, that is. It's not actually a linear map. Right? So its determinant is only well-defined modulo squares. But fortunately, if you look at the way the determinant occurs, it occurs in one of these Legendre symbols. Remember, this is the number that's 1 if this is a square mod P, and it's -1 if it's another square mod P. So it's just a sign, but it only depends on the class modulo squares. So it's well defined. So it's like a determinant occurring inside Gaussian integrals, but fortunately it only depends on the quadratic form. So that map in general may have a kernel, right? So I'm calling A the dimension of that whole space of representation, B the dimension of the kernel. Then that map will induce an isomorphism from H1 modulo kernel to this image. But if you go through the dualities, this is exactly the dual. The image is the dual of H1 modulo the kernel. So that's the guy whose determinant we're actually taking. Sorry, I said it's slightly misleading way a moment ago. And the A's and B's now I've explained as well. And that's the power of I. Now, I didn't explain this last thing, and I'm not going to explain it because this takes, again, a bit of machinery. These are linking numbers between the primes. These are arithmetic linking numbers. So, and they are defined essentially exactly the way you define it in three-manifold topology, except you have to interpret these symbols. It's possible to take the inverse of this thing, regard it as something like a current. So this is like choosing a Seifert surface for the prime and taking the linking. So one can make sense of all of these, but number theoretically, what you end up getting when you do this is various numbers that are related to something that people call p-power residue symbols. So these are these things that Hilbert symbols of a higher order that comes up in classical number theory. So as I said, this I can't really explain even on the surface. But for example, when p equals 2, they're closely related to these Legendre symbols that are viewed as mod 2 linking numbers between primes.
Were they called linking numbers before?
No. Well, I defined them, so I don't think they were called. These things, for p equals 2, it was called linking numbers, and people studied it extensively. These higher things, I guess I named them recently. So now let me go back to the formula a little bit. So these are linking numbers, and I've explained this determinant and all the numbers that occur. So of course, so many of you will recognize there was a formula of this sort proved by Schwarz in the early 1980s, I guess, long before Ed Witten's work on topological Jones polynomials and so on, right? So this was the first occurrence of not linking and so forth via path integral, and this is the analog in arithmetic. Let me give you a concrete case of it, just to give you a sense.
Abelian analog.
This is all abelian, that's right. So this is exactly the abelian. So as I said, the work of Schwarz from the.
Can you really not tell us a little bit more? I mean,
Sure.
So much of the beef is in this linking.
I know, yeah, that's right, yeah. So you can compute them using, again, these are defined using class field theory. Maybe after, we can talk about this at the end if we have some time. Yeah, no, yeah. So, well, I'm very glad that you're interested, by the way. I'm happy to discuss this further. It's a little bit technical, the definition. It's you can think of them as generalizations of these Legendre symbols for now. Okay. Right. Okay, maybe one way. In simple cases, maybe I can say it in some way. It's not exactly that because you have to deal with all these equivalence classes of ideas. But if you take two primes, you can roughly think of it as looking at the field generated by nth root of one prime, right? And letting the Frobenius of corresponding to the other prime act on that thing. And so you get a root of unity that way. So that's roughly the flavor of these linking numbers. Okay, now here's a concrete example. Suppose f is the field generated by the p square roots of unity. And I'm going to make a rather restrictive assumption. This occurs not infrequently. These are called irregular primes. But anyways, I'm going to assume that inside the ideal class group, the p part is exactly z mod p. In that case, the previous path integral, now this is without the insertions, just gives rise to this classical Gauss sum that goes back to Gauss, of course, right? And so this is rather interesting. So I guess what I'm doing here, of course, this formula was proved by Gauss, and actually it was reasonably hard to prove this. So this second formula he proved first. And this one he was interested in because somehow the quadratic reciprocity follows immediately from this formula. This is one of his many proofs of quadratic reciprocity. But then to move back from here to get the sign exactly right was quite hard. So it's not that we're giving a new proof in any sense, because implicitly we're using all this machinery. But I guess what I'm doing is giving a path integral interpretation of this formula of Gauss, right? Which somehow, again, at a very vague philosophical level is somewhat interesting because, as you know, there's this geometric Langlands, which of course Ed Witten and other people have worked on, as it's coming out of these dualities in quantum field theory, right? In number fields, quadratic reciprocity in some sense is the first case, the simplest case of Langlands reciprocity, right? And that's in some sense, that's just a path integral formula and nothing else. Yeah? So is there an interpretation? Now we can go back to the fancy machinery over in the geometric situation and somehow give a similar interpretation of a duality sort to the simple path integral. I don't know, that's probably a stupid question, but I can't help mentioning it briefly. Okay, now there's the case with boundaries. I see that I'm running short on time, so maybe what I'll say here is so this is supposed to go to 45, right?
No, I mean,
Yeah.
say what
All right, yeah. Right. So here, we know what's supposed to happen in TQFTs or Chern-Simons series. So that's XS. That's where you remove finitely many primes. That's supposed to be, remember, like removing tubular neighborhoods of knots. So you get a manifold with boundary. And so the pi 1 is this absolute, unramified outside as absolute Galois group. And pi 1 of the boundary components are these local Galois groups, remember? Now, embeddings of this, the Galois group of the algebraic closure of F into FV, the algebraic closures of FV, they induce these morphisms from these local Galois groups to global Galois groups. Right? And we need some technical assumptions. Now, to define the Chern-Simons function in this case, we need to choose an actual cocycle rather than a cohomology class, as happens for 3 manifolds. But otherwise, the theory is exactly the same. So in addition to the global moduli space of representations, right, from pi s to A, we have these local moduli spaces, collection of representations of all these local Galois groups, right, into A, modulo gauge transformations again. And of course, given a global representation, we can restrict it to a collection of local representations. Right? I wrote /A because you can view the whole thing as a groupoid as well, but I'm not going to belabor that point. Now, given any collection of local representations, that's what I'm writing as phi sub s. If we pull back the cocycles to these local Galois groups, remember, well, maybe I didn't say this. This local cohomology is 0 beyond H2, exactly the same as for 2 manifolds for Riemann surfaces. So that class can be trivialized. So if you look at those things whose boundary is equal to this class, right, inside the 2 co-change modulo, the 2 boundaries, that forms a torsor for H2. Right? That's a principal bundle for H2, right? We're looking at the solutions to these equations, right? You think of it as kind of like a differential equations, modulo exact solutions, and difference between any two lies inside the kernel of the mod exact solution. So that's a class of H2. And remember, this was supposed to be 1 over nz mod z. So these are numbers. So that happens at each v. So if you take the product over all v, you get a torsor for the product of 1 over nz mod z. Right? And now you can use the sum map to push this out to get a single 1 over nz mod or z mod n torsor over the space of local representations. Right? So you get that's kind of the analog of these line bundles that occur in Chern-Simons theory. Of course, you can turn it into an actual line bundle by exponentiating. Yeah? Then these elements, 1 over nz mod z torsors will turn into mu n torsors for roots of unity, so which can be viewed as inside S1. So you can actually get a complex line bundle over the space of local representations as well. Okay? That's how denoted by L. Now, but if you have a global representation, not just a collection of local representation, you can also solve this equation globally for group cohomology of pi s of this fundamental group of ring of S integers. That's because this H3 of the whole ring of integers is one-dimensional. But if you remove a certain suitable collection of primes, it actually becomes 0. H3 becomes 0, and it only survives up to H2. So in fact, this can be solved globally. And then you can take this global solution, restrict it to the local moduli spaces, and apply this sum map, so you get an element of this local torsor. And so it's a consequence of this reciprocity sequence that I mentioned earlier, which, as I said, encapsulates global class field theory. That implies that this Chern-Simons element is independent of your choice of solution. It only depends on the representation. And so, somehow, so this, even though it's simple, the way I stated it here, other than these facts that I'm throwing at you, I think it's quite interesting that the independence of this Chern-Simons class really is using the full strength of class field theory, global class field theory. So what we are getting is a canonical section of over the global moduli space of representations of the torsor over the local moduli space pulled back by the restriction map. As you get, again, in topological Chern-Simons theory. Now, there's a decomposition formula, but maybe I'll skip that because you can prove that in exactly the same way you would do it for...
Usually, decomposition formula, you split a 3-member
That's right.
pieces.
That's right, yeah.
But here, you really take all the primes, throw it on here.
So what you do is you remove these primes in S. So you can remove more if you want, right? And then you can view the whole ring of integers as being that thing glued with the ring of these completions at the primes that you've removed. Then they intersect along the spectra of the local
So
field.
you glue a big 3-manifold with small...
With small 3-manifold, that's right. Exactly, that's right. So this is the kind of, what you're mentioning is exactly the kind of thing that's missing here, where you are able to glue really very big 3-manifolds. You can formally do this by gluing sort of S integers inside completely different rings together. That's a fun thing to do, but I haven't thought about it too much. That's right. So anyways, there is a decomposition formula which is still allows you to compute, even though that what you say is exactly true. This formula does allow you to make computations, and we've done some computations and applied it to sort of somewhat classical sounding problems of number theory. But maybe I'll skip all that and so-called embedding problems. But I'll skip that and instead mention the path integral in this case. Well, see, of course, in topological Chern-Simons theory, what would we do? We'd fix a boundary state, right? And then consider the integral over all the global states that restrict to that boundary state, right? And then as the local representation varies, you get a section of this line bundle that lies over the local moduli space, right? So this is, in the TQFT view, the state that your manifold with boundary assigns to the Hilbert space of the boundary. So I'm not going to say much about this. We do use it for certain computation, but I guess I won't dwell on that today. But I will make a few comments about the structure here, just to, in case you're interested in this, how far the analogy goes. We can keep taking this further and further. But for the moment, I will remark the following. The simple case, remember, I discussed the case where A is just the abelian group Z mod P. In that case, this local moduli space, remember, it's just this product of H1 with this local Galois groups with coefficients Z mod P actually is a symplectic vector space in that case. So, but this symplectic vector space structure is also a fairly deep fact. This is another version of the local class field theory I mentioned earlier. The fact that you get a alternating perfect pairing between H1 that ends up in this H2, which is Z mod P again, that is, again, another version of local class field theory. So it becomes a symplectic vector space. Furthermore, now again combining with global class field theory, the image of the global representation inside the space of local representation is actually a Lagrangian subspace. So that's, again, highly parallel to the 3-manifold theory, but requiring substantially more machinery, as I said, because it's a kind of the hard part of graduate level algebraic number theory. So then, when you do this integral, what you end up with is a section over this isotropic subspace of this line bundle, of course, which is the natural quantization of the symplectic vector space. And so I haven't done much with this yet, but it's interesting because, of course, then this symplectic vector space, there is a natural action of the Heisenberg group and metaplectic representations over finite field that applies the same way it works over C. So it's interesting to investigate this interaction with this Chern-Simons invariant, but which I haven't done right now. There are other things you can do. You can fix other Lagrangian subspaces as boundary conditions, right? And try to get numbers out of this and observe the interaction. as you run over different global number fields that have the same local completions. So this is another way. You get different Lagrangian subspaces, different state vectors, as you run over different number fields even. So those are all subjects of study in this direction. But simply because my powers of computation have been so limited, I haven't really been able to look into it at the moment. So if we had time, I was going to go into some of the motivations for this. One motivation, I think there are many things that come out of this other than just curiosity about the parallel structures. Actually, the main thing that I was interested in is that there's another global function that number theorists have been very much interested in. In a sense, I don't know why we're interested in it. These are called L functions, right? They somehow associate a complex invariant to every representation, right? And it's regarded as a central object of study in number theory, L functions. And they're mysterious. And they're very useful. Their utility comes out of the tradition somehow. But fundamentally, why L functions are so useful is quite mysterious even to me. Actually, do you know why they're so useful? Anyways, you can ask him later. But anyways, wishful motivation, which is probably won't work out, is that I'm feeling like these Chern-Simons type invariants, which are easy to define invariants associated with color representation, will give us some insight on these very difficult invariants, like L invariants, L functions associated to representations. So there's a long story behind this, which maybe I'll spare you for today. Thank you very much.